Hidden beneath a glossy swatch of fabric is a chemical miracle. Long chains of repeating amide links, thousands of units long, carrying load like microscopic steel cables. This is nylon, invented in a lab where polymers that behaved like silk were once thought impossible. In the 1930s, chemists stitched molecules together with surgical precision, controlling reactions to build chains with predictable lengths, melting points, and strength. Nylon is not woven from animals. It is formed from liquid polymers, forced through tiny holes, then stretched and set so the chains align. The engineering challenge is staggering. Keep reacting molecules hot enough to flow, but cool enough to avoid breaking chains. Remove water vapor that shortens the polymer, force molten polymer through spinnerets with holes measured in micrometers, and pull fibers at speeds of thousands of meters per minute without snapping them. Every temperature, every second, and every atmosphere in the reactor changes the final fiber. The invention turned chemistry into manufacturing, and a lab curiosity became an industrial product that could replace natural silt. In this chapter, we map the anatomy of nylon, from monomer chemistry to the fiber's microscopic alignment, and explain why each controlled step is essential for that silk-like feel. Nylon begins far upstream, in the fractionating towers and cracking furnaces of the petrochemical complex. Crude oil and natural gas are separated into naphtha and other streams, then steam cracked to produce light hydrocarbons. From those streams, chemists build the specific monomers needed for nylon. For nylon 6, the two key building blocks are adipic acid and hexamethylene-diamine. Adipic acid is produced from cyclohexane or benzene derivatives through controlled oxidations and purifications. Hexamethylene-diamine comes from adiponitrile hydrogenation using catalysts under hydrogen pressure. For nylon 6, caprolactam is synthesized from cyclohexanone oxime via the Beckmann rearrangement. Purity is critical. Traces of water or acids cap chains and lower molecular weight, making weaker fibers. Plants wash and distill monomers to food-grade cleanses, then dry them to molecular dryness, often down to parts per million of water. They store monomers under inert gas to prevent oxidation. The transformation from crude fragments to pure chemical building blocks is brutal. High temperatures, strong oxidants, catalytic hydrogenations, and careful fractional distillation. Each step concentrates chemical order out of chaotic oil fractions, preparing the raw molecules that will link into the long, load-bearing chains we call nylon. Polymerization is where chemistry becomes macroscopic material. For nylon 6,6, manufacturers first make a nylon salt by neutralizing adipic acid with hexamethylene-diamine in water. The salt is dried, then heated under vacuum in a reactor to drive the condensation reaction. Water is expelled as each amide bond forms, and operators control temperature to keep it flowing yet stable. Typical melt polymerization temperatures are around 260 to 280 degrees Celsius under reduced pressure to pull off water and push the reaction toward longer chains. For nylon 6, the route is different. Caprolactam undergoes ring-opening polymerization at temperatures near 240 to 260 degrees Celsius. In both cases, the goal is long chains, measured by intrinsic viscosity or melt flow index. The longer the chain, the higher the molecular weight, and the stronger the fiber, up to a point. Crystallinity forms as chains pack in lamellae. The degree of crystallinity controls stiffness and melting point. Throughout polymerization, engineers monitor torque, viscosity, and byproduct concentration. If molecular weight is too low, the fiber will pill or break. If too high, it will be unprocessable. The reactor is a tuner of material properties, converting monomers into a molten mass with the memory of silk. Turning molten polymer into continuous fiber is a lesson in fluid mechanics and precision machining. The polymer melt is fed into an extruder, a heated screw that plasticizes and pressurizes the polymer. It is forced through a spinning pack and then through a spinneret plate, a hardened tool with hundreds to thousands of tiny holes. Each hole is typically in the range of 100 to 500 micrometers across. At 250 to 280 degrees Celsius, the polymer exits as molten jets. Immediately below the spinneret, a quench chamber with controlled cooling air solidifies the filaments into fibers. Control lines adjust air velocity, humidity, and temperature. Too rapid cooling locks in amorphous structure. Too slow allows sagging and breaks. Take-up wheels pull fiber at speeds of up to 2,000 to 3,000 meters per minute, stretching them gently as the extruder maintains constant pressure. Spinnerets are precision ground because a microscopic imperfection creates a weak point. Filaments can be made as single continuous filaments or grouped into multi-filament yarns. Melt spinning is a mechanical ballet. Pressure, heat, and breath conspire to turn viscous polymer into the filaments that will become textiles. The raw filament is weak until it is drawn and oriented. Drawing stretches fibers to align polymer chains along the fiber axis, converting curly random coils into taut, load-bearing rods. This alignment is the origin of nylon strength. A freshly spun filament passes sequentially over heated godettes, metal rollers that control temperature and speed, then is pulled with draw ratios commonly of 3 to 6 times its original length. Temperatures during drawing are often between 120 and 180 degrees Celsius, hot enough to allow chains to slide and reorient, yet below the melting point. The drawing process increases tensile strength, raises modulus, and reduces elongation at break. It also increases crystallinity, forming fibrillar structures visible under electron microscopes. Engineers watch draw tension, speed differential between rollers, and filament temperature. If tension spikes, filaments snap. If the draw is too mild, the fabric will lack resilience. After drawing, fibers often undergo heat setting to lock in molecular order, typically at 150 to 200 degrees Celsius for several seconds. Drawing is invisible forging, pulling order out of a viscous tangle to achieve the mechanical properties that make nylon behave like silk. After drawing, nylon is still pristine and slick. To make it useful in apparel and carpets, manufacturers apply textures and finishes. Texturizing introduces bulk and stretch. One common method is false twist texturing, where yarn is twisted, heated, and untwisted to create permanent crimps. Another is air-jet texturing, which uses turbulent air to tangle filaments into bulky, wool-like yarns. For fine silk-like stockings, manufacturers control denier, mass per length, down to very low values. Finishing adds lubricants, anti-static agents, and heat-set treatments to stabilize dimensions. Dyeing is a chemical handshake. Nylon is a polyamide with amino groups that accept acid dyes. Dye houses control bath temperature, pH, and liquor ratio to ensure even uptake. Typical dyeing takes place at 80 to 100 degrees Celsius, with pH adjusted for optimal bonding. After dyeing, yarns are rinsed, dried, and sometimes coated with silicone for hand feel. Each additive is chosen not to weaken fibers or alter melt behavior. Texturing and finishing convert a straight, glassy filament into a tactile yarn, soft, elastic, and colored, ready for fabric formation. Every surface treatment is a trade-off between look, feel, and durability. Nylon's journey continues on knitting and weaving machines that convert yarn into fabric geometry. For hosiery, circular knitting machines with fine-gauge needles form continuous tubular fabric at high speed. Gauges measure needles per inch and determine fineness. For broader textiles, weaving looms shuttle warp and weft or use rapier and projectile techniques to achieve tight, even cloth. Machine speeds vary. Circular knitters can run at thousands of revolutions per minute, producing meters of fabric per minute. Stitch density, yarn tension, and needle profile are tuned to avoid runs or snags. Seamless garments use warp knitting and seamless circular machines that reduce weak points. For carpets, tufting machines push yarn through a backing and then lock it with latex and secondary backing. Heat setting stabilizes the final fabric dimensions. Throughout, humidity control in the mill affects nylon's moisture regain and static behavior. Operators watch run lengths, knotting stations, and online defect detectors that flag broken yarns and loop faults. The mechanical choreography of needles, shuttles, and rollers transforms engineered filaments into the textured surfaces we touch every day. Nylon must survive real-world abuse, so quality control is built like a torture lab. Automatic optical inspection systems scan yarn and fabric at production speeds for density variations, thin spots, and foreign particles. Laboratory tests quantify mechanical performance. Tensile testers pull samples to failure, measuring tensile strength and elongation. A typical high-performance nylon fiber will show tensile strengths in the range engineers expect for durable textiles. Denier is measured as mass per length, grams per 9,000 meters, and determines fabric weight and drape. Thermal analysis identifies melting point and glass transition, while differential scanning calorimetry measures crystallinity. Color fastness labs run wash, light, and perspiration tests to measure dye stability. Abrasion testers simulate repeated rubbing, and aging chambers expose samples to UV light and elevated temperature for accelerated life tests. Chemical analysis, like Fourier transform infrared spectroscopy, confirms polymer identity and detects contaminants. Every failed sample informs process adjustments, tighter drying, different draw ratios, or spinneret maintenance. The goal is repeatability. Produce millions of meters of fabric with predictable hand, strength, and color, batch after batch. Industrial nylon production is powerful, but it carries chemical and environmental challenges that engineers must solve. Adipic acid manufacture commonly emits nitrous oxide as an unwanted byproduct. This is a potent greenhouse gas that modern plants capture or destroy with catalytic abatement. Hydrogenation steps use pressurized hydrogen and flammable solvents, requiring explosion-proof equipment and strict safety interlocks. Waste streams contain organic load and require biological or chemical treatment before discharge. On the product side, nylon is not rapidly biodegradable. End-of-life textiles create landfill mass unless recycled. Mechanical recycling chops and remelts post-consumer nylon, but quality degrades with each cycle. Chemical recycling, breaking nylon back to caprolactam or adipic acid and resynthesizing, requires energy and selective catalysts, but can restore virgin-like properties. Energy efficiency matters. Process heat recovery, electric drives on extruders, and optimized distillation cuts carbon intensity. Regulatory compliance and life cycle analysis now guide plant upgrades. Engineering solutions are practical, capture emissions, tighten seals, replace solvent steps, and design for recyclability, turning the industrial-scale advantage of nylon into a more sustainable pathway. The final triumph of nylon is scale and versatility. What began as a laboratory polymer is now in parachutes, airbags, carpets, toothbrush bristles, and, famously, stockings that replaced silk. Engineers tuned molecular weight, draw ratios, and finishing chemistry to hit targets: strength, elasticity, sheen, and hand. Compared to silk, nylon offers consistent properties, lower cost, and mass manufacturability. Nylon 6,6 melts around 265 degrees Celsius, and Nylon 6,6 melts around 215 degrees Celsius, giving processors different windows for melt processing. Its semi-crystalline structure provides toughness and abrasion resistance, while chemical affinity for acid dyes creates bright, durable color. The final product is a system: chemistry, reactors, extrusion, drawing, texturing, and finishing, all linked in a production chain. Each link must be engineered, instrumented, and controlled. The result is synthetic silk, engineered fabric that mimics nature, but at a scale and price nature cannot match. Nylon's story is a chronicle of chemical engineering, mechanical precision, and iterative problem-solving, and it remains one of the great manufacturing achievements of the 20th century. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.